Hello and welcome to our demonstration of Part 1 code. My name is Ethan
And my name is Ahmed.
and we'll be taking you through our code for Part 1 in the assessment. Now, the report goes into great detail about our code and different problems that we've faced going through it, but this will just be a general overlay of our code. So initially it takes an image and loads it into our algorithm. Then by taking the size of the image, we can use the rows and the columns to step through the pixels later on. Sometimes our inputted image was actually not black and white, a binarized image, it was grey. So this section of code here will identify this and edit the image so that it's only ones and zeros. It will then leave a comment like this one down here in the command window at the bottom, identifying if the image is black and white or if it's been adjusted. This next section of the code is used to help improve our image, because sometimes if there's white pixels around the edge, these can't be deleted by the way the code works, so it can ruin the quality of our image. So by setting these to black, which is 0, we help fix this issue. We have one big for loop, known as k, with the number of iterations, the number of times it goes through part 1 of the code and part 2 of the code. Here we have a variable called sum of rules, which is used to determine if one of the rules has been met, 2, 3, or 4. This can be used to mark pixels for deletion. We then use two for loops to step through all of the rows and all of the columns, with pixel 1 being known as position XY. Condition A from the lab sheet has been converted into this sum here, with if this rule is true, then the correct pixel location will be add 1 to show that this rule has been met. The same as for condition 2 taken from the lab sheet. Here we use a function called parts b1, which simply brings us down to the bottom of our code. All this is a simple implementation of the condition that is shown in the lab sheet. Condition B looks for any changes from zeros to 1, and if only 1 in the entire ring is found, then our sum of rules, our condition is met, so we add 1 at the pixel location. C and D are very similar to what we've seen before. All it does is take the condition from the lab sheet, implement it into the code, and if the condition is met, which it has to be equal to 0, then we'll add 1 to the sum of rules at the location of pixel 1. Once we've gone through all 4 conditions for part 1, we look at our sum of rules matrix. This is to tell us if all conditions have been met. If all 4 conditions have been met, then we mark the pixel for deletion with a 0. Once this process is completed, our image will look slightly different from initially. We then reset sum of rules, and we complete the process again for step 2. With 2 for loops to step through all the pixels, condition A and condition B are exactly the same. Condition C' and condition D' are implemented exactly the same as C and D as shown in part 1. At the end of this code, we again have a sum of rules. This final end here is the end of the loop, and this is where we will continue to go round until the number of iterations is complete. In this case, we have 325. We then output our original image and the skeleton image. An example of this code being run, I will first implement with this maple leaf provided in the lab sheet. By clicking the run, it will run through it. In the command window here, we can see the image is identified as black and white. This is telling us that the image will not be modified in any way to try and binarize it from ones and zeros. Once the algorithm is complete, if it's a black and white image, it will output two figures. The first one, the original image. Here we've got this maple leaf. And on the right hand side here, we've got a very high quality skeleton structure. Thank you very much for listening to part 1, and please return for part 2. Welcome to part 2 of our assignment. For part 2, we split it into 3 different codes. This was just from reading through the lab sheet and determining the best way that we can improve our skills and also complete the lab exercise. Our first section is looking at the previous code to draw the outline. Our second code is looking at the number of descriptors and see what that does. And finally, our third code looks at the properties of the Fourier descriptors. This video will only be going through using the previous code, and I'll only outline the parts of the code that we have changed. As declared at the top, we edited the fd.m code that was provided in the lab, and we used our part 1 code to approximate the outline of the shape. So the only part here that has changed is the start, where it draws the outline of the shape. Originally, it uses a Gaussian filter and then reverses the image to draw and approximate the outline. However, we use our part 1 method with some alterations. The first alteration here that you'll notice is our for loop only has one cycle. That is because we're only trying to highlight the outer pixels and not trying to get rid of them to draw a skeleton structure. We again continue to use sum of rules in order to show which pixels we're wanting to get rid of, but in this case we're using it to represent the ones we're going to keep. Image 2 is our image for the outline of the shape. We again exactly the same for step 1. We go through and step through all of the pixels for X and Y. Condition A, B, C, and D are the same. However, our comparison statement is now different. Here, when all 4 rules have been met, conditions, we actually mark a 1 in our image 2. This is where we're trying to draw the boundary condition. We again reset the sum of rules, and step 2 is exactly the same as part 1 code. We have condition A, B, C dash, and D dash. Again, we've got the same sum of rules equal to 4, so all 4 conditions are met, and we simply add 1 to the same pixel location in our second image. Finally, to decide the complete outline of the object, we use a new function called image2out. Here, where our image 2 is equal to 2, that means pixels have been highlighted to be kept in both part 1 and part 2. At the same pixel location, we mark a 1 and our boundary is drawn in. The rest of the code below here has been taken straight out of fd.m, as we were only trying to demonstrate that we can draw the outline of the object using our part 1 code. I will now give you an example of running the code with the triangle image. So it first brings up our original image. So this is the triangle. Our part 1 code has effectively drawn the outline of our triangle here. And then the fd.m code that we have taken across approximates the outline of it. This is with 8 descriptors points. Our next examples will go through the properties and how the number of descriptors changes to give us a greater understanding of how this all works.
In the second section of part 2, we changed the number of descriptors. We edited the fd.m file. In the fd.m file, we changed to Umax. Umax is the number of descriptors, or number of points on the approximation line. Using a geometric sequence, number of descriptors were varied, starting from 1, finishing at 16. This provided with a general indication of how many descriptors would be required for the outline to show a better representation of the image. I will now do a simulation of the noisy chromosome. To get rid of the noise in the noisy chromosome, we use a Gaussian filter, and then we binarized it to be black and white. This allowed us to get a better output of the image without noise. As you can see, when we have Umax equals 1, the output of the outline is much different. When we have Umax equals 2, you can see the outline is trying to replicate the original image, but there's not enough descriptors for it to do so. When we increase the number of descriptors to Umax equals 4, the output is closer to the original image, but is still not going through all the corners of the image. When Umax is increased to 8, it gets a much better output than before. It is reaching most of the corners of the image, but there are still some problems with it. As you can see, there are some dips which it doesn't go through, so some of the information is lost. When the Umax is increased to 16, there's a much better output. The outline covers all the dips and curves of the noisy chromosome, but there are still some bits which it misses out. Increasing the Umax even more would give us a better output. Next, we look at the invariance property. First off is the identity. The identity property has already been implemented, shown in the previous code. This time, we added 32 descriptors to get the most accurate boundary for the identity property. The property after identity property is the rotation property. The rotation property was implemented using the rotation formula from the slides. The rotation property changes the orientation of the output, rotating at anti-clockwise at a provided angle in radians. The next property is the translation property. The translation property was implemented using the formula in the slides. This property will draw an approximation of the outline offset by the given x and y coordinates. The next property after translation property is the scaling property. Scaling property scales the outline, making it bigger or smaller depending on the inputted value. Last property is the starting point. We couldn't fully get the starting point to work. The starting point basically changes the point at which the outline starts at. This could mean that it would start at more desired location than before. Now I will do a simulation of the chromosome. First of all, we can see the identity property as before, but with the 32 descriptors we can see it clearly outlines a much better output than before. Next is the rotation property. We can see the outline being rotated at 45 degrees. After the rotation property is the translation. We can see the outline is translated at x 100 and y 100, outputting at a different place. After the translation is the scaling property. The scaling property, we can clearly see the outline has been scaled to a smaller value. The starting point is not currently working. If the starting point was working, it would change the point that the outline starts at, meaning it could start at a different location.